In this video, we discuss systems of linear equations. In general, matrices are rectangular arrays with rows and columns, and there are a specific special family of matrices that are called square matrices because the number of rows is equal to the number of columns. So, and among that family of square matrices, there is a particular group of matrices. They are called identity. They have ones in locations that are entries where the row and the column number, row 1, column 1, row 2, column 2, row 3, column 3. So the number of the row and the column matches. And so that location is called diagonal. I should put some dots here in between. And so they have ones on the diagonal and they have zeros everywhere else. So they have a lot of zeros. These matrices are they form a particular family. They are called identity matrices. In fact, you could think of these locations of these ones as forming a shape or defining a shape that looks a little bit like a staircase. So you write a big zero, there are lots of zeros above the diagonal, lots of zeros below the diagonal. This is an identity matrix. And for sake of illustration, a matrix with 3 rows and 3 columns. See, the first column would have entries 1, 0, 0. The second column would have entries 0, 1, 0, and the last column would have entries 0, 0, 1. This would be an identity with 3 rows and 3 columns. So let's take a look at a matrix that has 8 rows, an identity with 8 rows and 8 columns, and 8 by 8 identity. So I'm going to put this on the first column, and then I'm going to, this is arbitrarily, maybe I select column number 6 there, and then the very last column. Okay, so I am kind of highlighting 3 particular columns. So I'm going to give each of these columns a specific name. I'm going to use the notation E. So I'm going to say the first column is called E sub 1. Column number 6 is going to be called E sub 6. And the very last column here is going to be called E sub 8. So E sub k denotes the kth column of the identity matrix. Specifically with the highlights I have in the previous case. So E sub 1 has 1 on the first entry, zeros everywhere else. And then we have E sub 6. E sub 6 has a 1 on position 6, zeros everywhere else. And then we have E sub 8 with a 1 in the last position and zeros in all the other locations. These column vectors are special because they are orthogonal to each other. That's very easy to see. You can take the dot product, and because there are a lot of entries that are 0, these calculations are straightforward. So you take dot product between these vectors and obtain 0, so they're orthogonal to each other. And then the calculation of norm of the vector, the norm or magnitude of each vector, equals 1. So they have norm equal to 1 and they are orthogonal to one another. So it's very easy to see that E1 dotted with E6 equals 0, and similarly. So we also know that the square of the norm of every E sub k that would be equal to 1 square plus 0 square plus 0, which is equal to 1, and that implies that the norm of E sub k is equal to 1. So in other words, this is implying that the E sub k's vectors are they have norm, they're unit vectors. So with these properties, the vectors E sub k are actually called standard unit vectors. So the acronym RREF stands for reduced row echelon form. There are basically 3 main things involved here. One has to do with creating ones. So you like to create entries that are equal to 1, creating ones. You also would like to create zeros. And in the process, part of what you're trying to do is also to create a pattern that looks like a staircase. So the abbreviation REF stands for row echelon form, while RREF means reduce row echelon form. So in general, we start with a rectangular matrix. This is going to be representing an augmented matrix of associated with a system of linear equations. We would apply row operations, and there will be multiple intermediate row operations, but at the end you start with one matrix and then end up with a transform version of that matrix. Excuse me. And so this new transform matrix likely is going to have a lot of ones and zeros, right? At least that's what we would force or push for. And in fact, some of the columns of the reduced row echelon form are vectors like the so-called E sub k vectors. Some of the columns will happen to be standard unit vectors. But that it doesn't happen that every single column will be a standard unit vector. That pattern of the staircase with ones and zeros below and above in each of those columns, that is not always preserved. So it happens for some columns. Some other columns will not be standard unit vectors. So let's just put in maybe the format of a little bit of a recipe. So when we are going after solutions of systems of linear equations, you start with something that looks like in matrix vector form: AX equals B. A is the matrix of coefficients, B is the vector with the right hand side, the constants on the right hand side, X is a column vector with unknowns. So more or less AX equals B should look like a rectangular matrix A, a vector of unknowns X. We do have a requirement, and that requirement is that this number of columns needs to match the number of unknowns, right? So for AX to be a multiplication matrix, vector multiplication that's well defined, that we do have that requirement. So it may be that the system is not yet in matrix vector form, so we write a system in matrix form, then we create or form the so-called augmented matrix. That would be a matrix that has, so in general here, the coefficient matrix may have m rows and n columns. So this matrix, the augmented matrix, would be the same number of rows as in the coefficient matrix. The number of columns is increased by 1, so it has n plus 1 columns. If there are n variables or n unknowns, the number of columns in the augmented matrix is n plus 1. So once we have the augmented matrix, we compute the reduced row echelon form, and then out of that computation, then we would derive, we proceed to determine what are the solutions. So here we would have to rewrite the equations and address perhaps what is the general form of not only one solution. If there are solutions, maybe there is a general form as an entire set of possible solutions. There are some systems of linear equations that do not have solutions. Some of them have one solution and one solution only, and some of them support having not just one, but in fact many solutions, infinitely many.